Hello, my name is Deeksha Arya, and I will be presenting our paper, Traceability Network Analysis, a case study of links in issue tracking systems, co-authored with Alexander Nicholson and Jin Guo. An issue tracking system is a platform that allows users to upload bug reports, tasks to be completed, feature requests, and requests for enhancements for a particular project, among other issues that can arise. Jira software is one such issue tracking system. Here you see a screenshot of a typical issue on the Jira platform for the project Hive. What I would like to bring your attention to is this field issue links at the bottom. This issue, in fact, blocks another issue. And these relationships between issues are often manually created by members of the project team. So as this issue blocks another issue, the reverse relationship also exists, where the second issue is blocked by the first. Further, this second issue relates to a third. And these relationships between issues are called trace links. We can model the trace links between issues for a particular project as an issue traceability network, where in the network, the nodes are the issues themselves, and the edges are the trace links between issues. And as the number of issues increases within a project, and the number of trace links created for them or between them also increase, we establish this network structure. And this network structure can be used to inform information about issues and the relationships between them. For example, if A depends upon B and B incorporates C, we should be able to use the prior network structure to determine if there is or could be some relation between issues A and C. But not just the link types. Other information, such as the title or description, if semantically similar to others, issues, for example, should be able to provide us with some information on whether these two issues have some relationship. Prior work has looked at bug report networks and used them to assist triaging, which is the assignment of developers to bug reports for resolution. They have also been used to predict duplicate bug reports. However, bug reports are only one of the many types of issues that can exist, and duplicates is only one of the many trace link types that can occur between two issues. There has been no prior work on issue traceability as a network, and no studies to determine whether these issue traceability networks show salient properties or can be useful in performing issue traceability tasks, such as predicting links between the issues or relationships between the issues. And these pieces of information are very useful to inform other software development and maintenance tasks, such as the prioritization of issues or the assignment of tasks to developers. We hope to bridge this gap with our exploratory study, in which we identify and study the potential of issue traceability as a network. Specifically, we ask the research questions: do issue traceability networks demonstrate salient network properties that could assist in analyzing issues and their relations? And if so, to what extent can we leverage these properties for traceability tasks such as link type prediction? To answer our questions, we explore two characteristics of typical networks: the degree distribution, which is a quantitative value based on the nodes and the links in the graph, and triadic closure, which focuses on the relationships between issues within a network. And so we explore both the node and edge perspective of the issue traceability network. To perform our exploration, we downloaded the data of 66 open source projects from the Jira software platform. This resulted in a total of about 90,000 issues and 71,000 links. This graph shows the number of linked issues and trace links across the projects. You'll notice that a majority of projects within our dataset have the number of trace links and linked issues below 2,000, and only very few have linked issues more than 6,500. This table shows the most frequently linked types across all the projects in our dataset. The 4 in bold, relates to, duplicates, blocks, and is a clone of, are the 4 defaults that Jira platform provides. What's interesting is that custom created link types, such as depends upon and incorporates, actually occur quite frequently, even more so than the Jira default is a clone of. And they also occur in a large proportion of the projects in our dataset, 62 of 66. To measure degree distribution, we must first understand what the degree of an issue refers to. It is the number of links from this issue to other issues. The probability of a degree in a network is given by the total number of nodes that contain that degree divided by the total number of nodes in the network, and has been found in prior work to be an exponential value of the degree itself. Prior work has also discovered that when this exponent value, called the scale coefficient, lies between a value of 2 and 3, these networks are said to be scale-free. And this is visible in other domains, such as social networks. In our dataset, we found that 44 project networks have the scale coefficient value between 2 and 3, indicating that they are scale-free. A scale-free network means that as the size of the network grows, the properties and characteristics of the network do not change. A direct implication of a network being scale-free is that there exists a small number of issues that contain a large number of links. These issues are known as hubs, and the existence of these hubs are visible in the degree distributions of the scale-free projects within our dataset. Here you see an example of the degree distribution of the Hive project. You'll notice while a majority of issues actually have a very low degree, below 20, a small number have a very large degree, above 80, and these form the hubs in the Hive project. We identified hubs for each of the project networks as the most frequently linked issues that cover 90% of the trace links in a project. Among other findings, we discovered that hub issues take 3 times the number of days to be resolved in comparison to non-hub issues. And this is very interesting because the identification of hubs early on in a project can be useful in issue triaging and prioritizing the resolution of these hubs as required. We also discovered that a majority of non-hub issues are bug reports, whereas the majority of hub issues are improvements or new features. Both hubs and non-hubs have the largest relationship as relates to. And we believe this is the case because relates to is a generic relationship that somewhat subsumes all other link types. We then explored triads and triadic closure. A triad is a group of 3 nodes within a network. A closed triad is one in which all 3 nodes are fully connected, and hence they form a triangular structure. An open triad is one in which only 2 out of the 3 links exist. And so triadic closure is the property by which an open triad is converted into a closed triad by simply predicting the existence of the current non-existing link. For example, if A depends upon B and B incorporates C, from triadic closure we can infer that there is some relation between A and C. To determine the potential for triadic closure as in issue traceability tasks, We looked at the number of open triads with respect to the number of edges within each project network. We found that as the number of edges or the number of links increased in a project, so did the number of open triads. And this relationship across projects is exponential. This shows that triadic closure has a lot of potential for traceability tasks such as link type prediction. To determine whether this is actually the case, we performed link type prediction using triadic closure. We performed a training phase in which we calculated the closure measure of a link type link 3 given the prior link types link 1 and link 2. That is, for every triad that contains two links, link 1 and link 2, we calculated the closure measure of the for each possible link 3 type as the total number of closed triads that contain all three links divided by the total number of closed triads that contain link 1 and link 2, irrespective of link 3 in our training set. This table shows the top 5 heuristics by frequency across all the projects and their closure measure. A triad with 3 relates to relations occur the most frequent and have a closure measure of 88.74%. What's interesting, though, is that custom link types, such as depends upon and incorporates, form a triad with far less frequency, but a higher closure measure at 97.7%. What this means is that if A depends upon B and issue B incorporates C, then we can predict that A incorporates C with the confidence of 97.7%. To perform testing of triadic closure as a link type prediction mechanism, we perform testing across 2 scenarios, cross-project and within project. Cross-project indicates we treat all the issues in our dataset as one large network. Within project is where we perform our experiments for each of the projects and their networks. To perform the prediction, we say that for every node in the test set, if there exist 3 nodes A, B, and C, and 2 links between them, then we predict the type of the third link as the link type with the highest closure measure from the training heuristics. To determine whether the triadic closure can actually inform link type prediction, we measure its accuracy as the total number of correctly predicted links divided by the total number of links predicted in the testing set. To perform these experiments, we divide our training and test set into an 80-20 split. We achieved a cross-project accuracy of 71.88% using triadic closure, and this is far better than the random prediction baseline of 6.25%. We received a within-project accuracy of 60.56%, and that the cross-project accuracy is better than the within-project accuracy indicates that heuristics from within projects can actually be useful even to inform issue traceability tasks in the global context. And so with this, we show that a network property such as triadic closure can be used to inform issue traceability tasks such as link type prediction. To summarize and to answer our research questions, issue traceability networks do demonstrate salient network properties such as the scale-free property. This property implies the existence of hubs, that is a small number of very largely connected issues. The identification of these hubs early on in a system can help prioritize and triage critical issues. We were also able to leverage properties such as triadic closure for traceability tasks such as link type prediction and achieved a cross-project accuracy of 71.88%. And so with this, we show that network properties are useful in informing issue traceability tasks. To promote reproducibility and to encourage further research in this domain, we make our dataset publicly available. Thank you.